In this video, I want to do a quick relationship derivation for heat capacities in an ideal gas, as shown here. Cp minus Cv, the heat capacity at constant pressure minus the heat capacity at constant volume, is a constant R. This holds in the ideal gas, and it is surprisingly good for most real gases. Not all, but most real gases. So this is basically a four-step derivation. We're going to start with step one. And this is from your 7th grade. We're going to go with the heat equation. Delta Q is equal to NCP delta T. And then I'm going to advance this very quickly into college calculus, and then we're going to say dQ is equal to NCP dt. If you really have trouble with that little step, you might want to consider brushing up on your calculus before you do any more thermodynamics. All right, then we're going to go to a second step. In the second step, we're going to introduce the first law. The first law says that the change in energy is the change in heat plus the change in work. And then if we will hold pressure constant, that'll cause our change in work be minus PdV. And we're going to keep dQ, and we're going to keep du. Then we're going to take and make a substitution. dQ is NCP dt. We just derived that. So we go with du is equal to NCP dt minus PdV. And we will call this equation 1, and we shall remind ourselves that this is at constant pressure. All right, for step 3, we are going to introduce the gas law. Step 3, we're going to use PV equals nRT. We're going to take a derivative of both sides, so we'll have dPV is equal to the derivative of nRT. And we can do that at constant pressure. That becomes PdV equals N is a constant, R is a constant, and dt. And we can substitute this back into equation 1 for PdV. So that will give us du is equal to N, I'm sort of copying equation 1, NCP dt minus N R dt. There's the substitution. And then we'll divide through by dt, so we will get du dt is equal to, I suppose it's going to be NCP minus N R, which will become du dt is equal to N times Cp minus R. And we will call this one equation 3. Now for the fourth concept, we need to introduce a constant volume heat capacity. And at constant volume, the first law would give us du is N Cv dt, which again looks a lot like 7th grade thermodynamics. However, the first law would indicate that there is no work that's going to occur when we're at constant volume. So if we're going to write constant volume here for the dQ expression, we necessarily have no dW expression. Now let's do the same thing that we did in step 3 and divide through by dt. So we'll have du over dt is equal to N Cv. Now what I would like to do is to substitute this NCV into that spot. Since this is du dt and this is du dt, I'd like to substitute in. However, this is at constant volume, that was at constant pressure. Well, we have some good news. both of these variables, du and dt, are state variables. They do not depend on path. Therefore, it's perfectly okay to make this substitution. And so we can say that n cv is going to be equal to n times cp minus r. Well, look at that. The n will simply drop out from both sides, and that will be cp minus r. And then we can say cp is equal to cv plus r. And I think that's adequate to derive what we set out to do. Hope you can use this. Thank you for watching.